We've spent time on the vector calculus theorems, Green's theorem, Stokes' theorem, and the divergence theorem, and we've done examples where we convert a surface integral to a triple integral, right, or a surface integral to a line integral, or whatever it is, and those are fine. I'd like to show you one example of how these things are actually used by scientists and engineers, and often that is in a more theoretical framework. They're used to derive other results. So let's start with Gauss's law. Gauss's law from Phys 2 says that the flux of electric field through a closed surface, so closed surface, all of the electric field passing through that closed surface, the flux is equal to Q, which is the charge inside the surface, divided by some constant. So the flux through the surface is equal to the charge inside of the surface. That's Gauss's law. And how else can we represent total charge? We've been doing this all summer. It's in chapters 16 and 17. Total charge is the integral over the space of the charge density. Right? If we integrate the charge density, we get the total charge. W is the region inside this closed surface S. So that's another way of representing the total charge. And we put these two things together. In other words, charge is equal to this triple integral, and charge is also equal to the surface integral times a constant. So put these together, and we have the surface integral, or the flux of the electric field, is equal to 1 over this constant times the triple integral of the density of charge, dV. Now, on the left, this is a surface integral with a closed surface. We can use the divergence theorem. So here it is. Here's how the divergence theorem could actually be used in a more realistic setting. We use it right here. We rewrite that flux integral as the divergence of the vector field. So the divergence of E. On the right-hand side, we're still integrating the charge density. Now if I subtract, these are two triple integrals, so let's subtract the one on the right from both sides. We'll end up with a triple integral of the divergence of E minus 1 over epsilon naught rho dV, and that's going to equal 0. Subtracting from both sides leaves a 0 on the right-hand side. And this here, this is true for any closed surface S with an inside W. And since it's true for any region, that means what's inside has got to always equal 0. And this statement right here is one of the 4 Maxwell's equations. There are 4 Maxwell's equations, but this is one that relates the charge densities to electric fields. So that's one of them, and the others are derived in similar ways. And a lot of important results in electromagnetics, fluid dynamics, physics are derived from Green's theorem, Stokes' theorem, divergence theorem in ways that feel like this, like what we just did here. So that's a nice wrap-up. Shows an important use of the divergence theorem and derives an important result in physics and electromagnetic or electrical engineering. Sorry. That's it.